Section 10.3, Polar Coordinates and the Polar Coordinate System. So I love this topic. I think that it's really fun and really interesting. And there are tons of amazing applications to thinking in terms of the polar coordinate system. And this is kind of our new coordinate system that I've drawn out right here. This is like our substitute for the x-axis and the y-axis. And yeah, there are tons of really cool applications in physics. This is what we use in a lot of aerospace technology, robotics and fluid dynamics, and sound and acoustics. Like if you're someone who's purchased microphones before, you might have seen like these sort of cardioid patterns that are used to describe how microphones pick up sound and stuff like that. So there are tons of cool things that we could do with this coordinate system. So let's see how it works. The origin, okay, just getting ourselves oriented here. We have this point, we call this the pole, okay? You know, if you call it the origin, I'll know what you're talking about. But in the polar coordinate system, it's referred to as the pole. And the positive x-axis is called the polar axis. Okay, so you're probably used to orienting yourself like this when thinking about angles, right? Because we've worked with evaluating trig functions and using terminal points on the unit circle. So, you know, this, what we would usually call like our initial side, if we were orienting an angle in the Cartesian coordinate system, we're going to call this the polar axis. And coordinates now, rather than being given in the form x, y, you know, where it's an ordered pair where the first number is the x coordinate and the second is the y coordinate, we're going to use r theta. R is going to be the radius, which is the distance from the pole. And theta is going to describe the angle, right? The angle, basically how far we rotate from the polar axis. Okay. So to graph when r is less than 0, because sometimes we could have a radius value that is negative, what we're going to do is basically count units along the ray theta plus pi. Okay, so just a really quick example, you know, like if we're looking at the ordered pair, let's say -1 pi over 2, right? We'll find that angle, there's pi over 2. -1, we're just going to count in the opposite direction. So that's where that point is going to land right there, right? Or another way of thinking about that is rather than counting along pi over 2, we're going to add pi to pi over 2, and we'll actually be looking at 3 pi over 2. Okay, so we have a way, we'll see more examples very shortly, but we can have negative radii in this case. Okay, theta describes the angle whose initial side is the positive x-axis. We covered that. If theta is positive, we'll go counterclockwise, right? Which we're used to. Positive angles go that way. Negative angles will go that way, in the clockwise direction. So those are the basics. Let's get a little more practice here. So let's say I want to plot this ordered pair 1 pi over 4. So 1, that's my radius, right? That's going to be the distance of this point from the pole, and then pi over 4, that is my theta value. That's going to be the angle that, you know, the ray created by that point through the pole is going to make with the polar axis. So, okay, here's the polar axis, you know, that's like theta equals 0. So pi over 4 is going to be that angle right there, right? There's pi over 4. So I know that this ordered pair is going to be on that line there, but just a distance of 1 from the pole. So that's going to give me this ordered pair right there. So I'll label that. That's the ordered pair 1 pi over 4. All right, just like that. Quickly, I want to point out, so we could also represent this point in rectangular coordinates. What would this ordered pair be in rectangular coordinates? Well, I'm just going to tell you, this is the ordered pair root 2 over 2, root 2 over 2. right? If I was to just, in rectangular coordinate land, it's like we say, how far do you go in the x direction? How far do you go in the y direction, right? So see how I can kind of reduce this to a right triangle problem, right? This is like a 45, 45, 90 right triangle. So I could solve for those two side lengths. That's root 2 over 2, and that's root 2 over 2. So anyway, we're going to talk more about that in a second as well, but I just wanted to point out, the polar coordinate system, this is just an alternative to representing position in the two-dimensional plane. It's an alternative to, the x and y coordinate, that whole thing. We can also use r and theta. Okay, that's enough of that one. How about in purple ink, let's talk about this ordered pair 2, 3 pi. Okay, so where is 3 pi? There's pi, there's 2 pi, right, one full rotation, and then 3 pi lands us right here. Okay, so there it is, 3 pi is that angle right there. And this ordered pair has a radius of 2, meaning that, this point is going to be a distance of 2 from the pole, so there's our ordered pair. So 2, 3 pi. All right, and you could probably tell that, in rectangular coordinates, this would be the ordered pair -2, 0, right? Because it lies on the negative x-axis, if we're thinking in terms of rectangular coordinates. Okay, so there are those 2 points. Let's try a couple more. So this next one, let's do green ink on this one. So the ordered pair at 2, -pi. So the radius is 2, so I know it's going to be a distance of 2 from the pole, or from the origin. -pi, where is this angle? Well, this is if we go in the clockwise direction, just a half turn around. So there's -pi right there. Happens to be the same, the same line as 3 pi, or positive pi. And, okay, and we want a radius of 2, so boom, there it is right there. All right, and then just one more. This ordered pair at -1, 3/4. So here we've got a negative radius, right? So we have to do that thing where we kind of go in the opposite direction of the ray defined by this theta value. So first, 3 pi over 4, where is that? Okay, there's 1 pi over 4, 2 pi over 4, or sorry, 0, 1 pi over 4, 2 pi over 4, and then 3 pi over 4 is that ray right there. So here is 3 pi over 4. But since we have a negative radius, we're going to count 1 unit in the opposite direction. Okay, so 3 pi over 4 is that angle there, but we're going to count in the opposite direction. And that's how we, represent a negative radius. So there's the ordered pair -1, 3 pi over 4. Okay, so that's how it works, and we can see that, polar coordinates just offer an alternative to, the XY Cartesian coordinate system as a way of, expressing position in the two-dimensional plane. So polar coordinates have this kind of interesting thing going on where we have equivalent polar points. So for example, this ordered pair, 3 pi over 3. So that's just this point right here. There's 3 pi over 3. So notice that this is the exact same point as 3 -5 pi over 3, right? Because -5 pi over 3, that's just like, okay, there's -pi over 3, -2 pi over 3, 3 pi over 3, 4 pi over 3. -5 pi over 3 gives us this exact same ray here. Okay? So, if I go up a radius of 3, I'm going to end up with the exact same position. So this is the same as 3 -5 5 pi over 3. Another way that we could express this point is 4 pi over, radius of -3, theta value 4 pi over 3. Because, okay, where's 4 pi over 3? That is right here. Okay, so there's 4 pi over 3. What if we count 3 units in the opposite direction? We go 1, 2, 3. So notice that, these are just a bunch of different representations of the same point. So this kind of points out a big difference between polar coordinates and rectangular coordinates. Notice that with rectangular coordinates, just normal x, y, there's only one way to express, some point in the plane. But in the polar coordinate system, it turns out there are infinitely many ways to express a point, right? Because we can just add 2 pi to any angle and, end up with another theta value that yields the same position. Okay, so coterminal angles are y. We have infinitely many ways to express a point in the polar coordinate system. Something to keep in mind. All right, so remember back when we were plotting these points, I gave you a couple examples of the rectangular expression and the polar expression of the same ordered pair. But I didn't offer much of an explanation as to, how I was getting those. So here are some formulas that are going to help us do that. So converting between polar coordinates and rectangular coordinates. So we've got a couple of relations here that are going to help us with this. And I'm going to be referring to this picture here. So let's say that we've got this ordered pair r theta. Right, so obviously that's expressed in polar coordinates. So to represent this in terms of, Cartesian coordinates or in the xy coordinate system, it's like, okay, how far do we go in the x direction? How far do we go in the y direction? Right, so this is the same as this ordered pair x, y. Okay, so, let's say that I was, given the polar coordinates. Let's say I was given r theta and I wanted to express this in terms of x and y. So how can I do that? Well, looking at this right triangle here, I have theta, I have my radius r, so I can actually use trig functions to solve for x and y, right? So let's say I wanted to solve for x. Well, I know that cosine of theta is equal to adjacent over hypotenuse, so x over r. So just solving for x is equal to r cosine theta. All right, so notice if I had r and I had theta, I could use this formula right here to solve for x. Similar line of thinking, notice that sine of theta is equal to y over r. That's how I relate theta and y and r. And then multiplying both sides by r, I get y equals r sine theta. So these two formulas here, as long as we have r and as long as we have theta, we can plug it in and we can get x and y. Okay? So that is where these formulas came from. I just derived them real quick. So we'll use those to convert from polar to rectangular. What if we have the rectangular coordinates and we want the polar coordinates? Okay, so looking at the same picture here, let's say that I have the x and y coordinate. So I know what x is, I know what y is. So really I want to figure out what is theta, what is r. Well, to find r, this one's kind of easy. We can just use the Pythagorean theorem. Right? If I know what x is and I know what y is, then square x, add it to the square of y, take the square root, and boom, you've got r. So that's how we would get the r coordinate. Now how about theta? Well, notice that we can relate theta, x, and y using a tangent function, right? So tangent of theta equals y over x. So another way that we could think of this is like, if we have y and x, we're just solving for theta in this basic trig equation. So we might use, you know, an inverse tangent function or something like that. All students take calculus, whatever. So these two formulas are what we would use if we had rectangular coordinates and we wanted to convert to polar. So let's see a couple examples here. So for example 2, we want to express with polar coordinates, or we want to express this, you know, polar point in rectangular coordinates. So first of all, I might plot this. You know, this is the ordered pair. So the radius is 3, and theta is pi over 4. So pi over 4, that's, you know, that angle right there. And then let's just say 1, 2, 3 units away. So there it is. There's the ordered pair, 3 pi over 4. So the way that I like to deal with these problems is I just kind of like to think of it as a right triangle. You know, I just draw in like, okay, you know, here's my right triangle. And I just think, all right, well, the radius is 3, this angle is pi over 4, so I want to solve for my x and my y there. So I'd make a little right triangle picture just because I don't particularly like memorizing formulas. And by looking at this, I can just think like, oh, okay, well, let's see, cosine of theta is going to be equal to x over 3. Right, multiply both sides by 3. And I get that. So if you are one of those people who has a great memory, you could just memorize the formula and you could just write that down. But I just wanted to show you, you know, if you're comfortable with right triangle trigonometry, you don't really have to worry about memorizing things as much. So now just simplifying this, so cosine of pi over 4 is root 2 over 2. So I'm getting that my x coordinate is just equal to 3 root 2 over 2. So that's important. And then solving for the y value, so I can see that sine of pi over 4 is equal to y over 3. Multiply both sides by 3. So that's me using right triangles to solve this. You also could have just had that formula memorized. Up to you. So I get 3 times sine of pi over 4, which is root 2 over 2. So I get that y is also equal to 3 root 2 over 2. So then the ordered pair is going to be 3 root 2 over 2, 3 root 2 over 2. So there it is. That's how I would convert to rectangular coordinates from polar. So now for example 3, I want to express this point in polar coordinates, and I have this ordered pair 1, 1. So, okay, you know, marking the x and y axis since I'm in, you know, rectangular coordinate land. So there it is, there's the ordered pair 1, 1. All right, so again, I really like thinking about stuff in terms of right triangles, so I'm going to draw this in. But you could also just have these formulas memorized, you know, r squared equals x squared plus y squared. And tangent of theta equals y over x. But anyway, here's what my triangle looks like. So that's 1, this is r, and this is theta. So I'm trying to solve for r and theta. So I can see that the Pythagorean theorem relates, you know, x, y, and r. So r squared is going to be equal to 1 squared plus 1 squared. So I'm going to get that r is equal to, you know, technically plus or minus root 2. But since we're in, you know, really, I'm going to pick my tangent, or my, rather my theta value to be in the first quadrant here. So I'm just going to take the positive radius value. So really positive root 2 is what I want. Okay, and now working with, to find the angle theta, tangent of theta is opposite over adjacent, so tangent of theta is going to be 1 over 1. So tangent of theta equals 1. And I happen to have, this solution memorized here. I know that this theta value is pi over 4. So I can represent in polar coordinates this same point as root 2 pi over 4. So a quick note, remember there was this point in the problem solving for r where we had r was equal to plus or minus root 2. And I said I was going to pick the positive one because I wanted my theta to be in the first quadrant. But it turns out that I also could have represented this, another solution to, tangent of theta equals 1. Theta also could have been, pi over 4 plus pi n, right? There's like more than one solution to this. So I also could have represented this point as negative root 2, let's see, what would that be? 5 pi over 4. I also could have represented this point in that way. Okay, so I just wanted to mention this to kind of explain, this plus or minus thing here. And you'll have to make a conscious decision whether you're using plus or minus for your radius value. And that's going to depend on which theta value you pick. So anyway, there's, 2 correct answers really for this problem, since there's more than one way to express this point in polar coordinates. Okay. So we've talked about polar coordinates, just how do you represent some point, some position in the polar plane. It turns out we also have polar equations. And we're going to talk a lot more about these in section 8.2, and we're going to look at the crazy types of graphs that you end up with. But for now, we're just going to talk about okay, we've got some equation in polar coordinates. For example, r equals 5 secant theta. And what if I wanted to convert this into rectangular coordinates? And then we're going to, for this problem, describe the resulting curves. So here's the tip for, dealing with an equation in terms of r and theta and trying to get it back in terms of x and y. So remember, we've got these formulas here. R squared equals x squared plus y squared. So if you see an r squared somewhere, you can substitute in x squared plus y squared for it. If we have like r cosine theta, we can plug in an x for that. If we have r sine theta, we can plug in a y for that. And then if you, I guess have an a y over an x, you could replace that with the tangent theta. Okay, so we're kind of like keeping these formulas in mind. So the goal, if you're trying to go from polar to rectangular, is you're trying to recognize, you're trying to spot like these types of expressions. Is there an r squared? Is there an r cosine theta, r sine theta, tangent theta? You're hoping these things are going to pop up because you can make these substitutions. And sometimes we have to use a little algebra to get these things to pop up. So, in this example, r equals 5 secant theta, I'm not really seeing any of these expressions that I can just substitute in x's and y's for. So I have to do a little algebra first. Notice I can write this as, r equals 5 times 1 over cosine theta. Just using a reciprocal rule there. And if I multiply both sides of the equation by cosine theta, I get r cosine theta is equal to 5. And check it out. R cosine theta, I know from right here that I can just replace r cosine theta with an x. So x is equal to 5. So that's how I would represent this this equation in rectangular coordinate systems. So I'll put a box around that. And then what type of graph does this give? Well, this is just a vertical line at x equals 5. Right? So here I could just maybe draw a little sketch of the graph. 1, 2, 3, 4, 5, 6, 7, 8. So the graph of this is just this line right here. Okay, so if we were graphing in the rectangular coordinate system, this is the equation, x equals 5. In the polar coordinate system, in order to get this line, the equation would be r equals 5 secant theta. So pretty strange, I know, but there it is. All right, let's try another one. So this next problem, r equals 2 cosine theta. So we want to do the same kind of thing here. We want to try and manipulate this to get, r squareds or r sine theta or tangent theta, something like that, so that we can substitute and get rid of all the r's and thetas and be left with x's and y's. So here I have an r right here, I have a cosine theta over here. So it would be great if this was an r cosine theta over here. And I wouldn't mind if this was an r squared over here. So the trick for this problem is I'm going to multiply both sides of the equation by r. And I'll get r squared is equal to 2r cosine theta. And r squared, I'm happy to see that. R cosine theta, I'm happy to see that. Because r squared, that's just x squared plus y squared equals 2 times, and then r cosine theta, that's just x. Okay, so now what is this? What type of curve is this? Well, I think that we might be left with a circle here, and let me show you why. If I subtract 2x from both sides, I get x squared. I'm going to write it like this, minus 2x. I'm going to leave a little room here. You might be able to guess why. And then y squared, and this is equal to 0. So notice that I can complete the square here by adding 1 to both sides. And I get, perfect square trinomial in the parentheses, so I can write this as x minus 1 squared plus y squared is equal to 1. And that's a circle, right? This is in the standard form of a circle. This is a circle with radius 1. So, the center is this ordered pair HK, which in this case is 1, 0, and the radius is 1. So I can graph this. It's going to look like this. Let's see, there's 1, there's 2. This circle is going to look something like this. Let's see, I was trying to use my tool here that makes perfect circles for me. Let's try that again. Okay, so that is what it's going to look like. Okay, so I wanted to point out here, notice that the equation we started with, r equals 2 cosine theta, this is a very nice way to represent a circle. Notice that this is like a much cleaner, prettier equation than this one, right? The equation we usually use for a circle. So circles are a good example of a type of function, or type of curve rather, that might be better suited or better represented in polar coordinates. Okay? And that kind of foreshadows what we're going to focus on in the next section. Okay, one more problem here. Some curves are going to yield rectangular equations that are so nasty and they're so, just bad looking and hard to work with that we don't even deal with them until we have polar coordinates. Okay, and this is an example of that. So, we can convert this into rectangular coordinate system. So it's possible to express this in terms of x and y, but the equation that we get is going to be pretty bad. Okay, so this is going to be an example of a curve that is much better, much better suited in rectangular coordinates. Okay, so let's see how this one works. So I'm seeing an r here, and I'd like to see an r squared there. I'm seeing a sine here. I'd rather see an r sine there. So I think what I'll do on this one is same trick as the last problem. I'm going to multiply both sides by a factor of r. And I'm going to end up with r squared is equal to 2r, because I have to distribute that factor of r, plus 2r sine theta. Okay, so this is going all right. I've got my r squared here, I've got my r sine theta, so I know that those can be expressed in terms of x and y. But I have a little bit of an issue because right here I just have this radius r value by itself. Okay, so here's what I might do. I can first of all subtract 2r sine theta from both sides. And what I am doing here is I'm kind of just isolating this 2r, because what I can do now is I can square both sides of the equation. So I'm kind of just aiming at getting an r squared over here. So the left side of the equation, I'm not going to simplify. I'm just going to leave it as r squared minus 2r sine theta whole thing squared. And this is equal to 4r squared. So it's kind of a mess. It's going to be even more of a mess once I, substitute in terms of x and y. But I can do that now because, all right, this first r squared, that's just x squared plus y squared. And then minus 2r sine theta, I can replace r sine theta with y. Did I do that right? Yeah. And this whole thing is squared, and this is equal to 4 times x squared plus y squared. Okay, so simplifying this would involve probably multiplying that whole thing out on the left and doing a bunch of stuff that wouldn't really be that helpful to us anyway. This is sort of, I would call this like a lost cause, just because it's such a complicated equation. So this second part of okay, let's describe the resulting curve. I have no idea what type of curve this would be, right? So I'm just going to say no idea about the curve. Okay, I don't have a chance looking at this equation in terms of x and y. I don't have a chance at deciphering what type of curve that is. Really, my best shot at understanding the curve is by using the polar equation. Okay, so in the next section, 8.2, we're going to see how we can graph polar equations, and we're going to come back to the type of curve that is defined by this type of equation. So just to build suspense here, we're going to learn about this in section 8.2. But there it is. There's our really horrible, gross looking rectangular version of that equation. Okay, and then example 5, last example of this section, we want to convert the following equation to polar coordinates. Okay, so we've got this in rectangular form, and you might recognize this is the equation of a parabola. right? This is in the form x squared equals 4cy, where c is equal to 1. So I know that this is going to be a parabola. The focus is going to, I can tell this is a vertically oriented parabola. So, my focus is going to be at this point right here. My directrix is going to be this line down here. And remember, I've got these ordered pairs. Let's see, 1, 2, 3. Got these ordered pairs here and here. So anyway, yeah, this is a parabola. So I'm curious. Let's see what happens if we try to convert this to polar coordinates. Okay, so to convert to polar coordinates, there are, looking back to our formulas, there are certain things that we're, hoping to replace. So any x value can be replaced with an r cosine theta. I'm looking up here. Any y can be replaced with r sine theta. If we have x squared plus y squared, that can become an r squared, and so on. So what I am going to do here is I'm just going to replace x and y with, so I'm going to rewrite this as, so x can be replaced with r cosine theta, and then this is equal to 4 times y, which is the same as r sine theta. And I can try to simplify this a little bit. I can square this out, so I get r squared times cosine squared theta equals 4r sine theta. And I can divide both sides by r, and I'm going to do that because I can sort of simplify by canceling out one of these r values. And I get r cosine squared theta equals 4 sine theta. And the last thing I'm going to do is I'm going to divide by cosine squared theta to solve for r. Okay, so r we're going to see kind of behaves like our dependent variable. Notice that in these equations that we had an example for, r was isolated in all these. So, dividing by cosine squared. I get this, which can be simplified even more because, this is 4 times sine over cosine. Using one of those cosine factors gives me tangent theta. And I'm left with one more cosine in the denominator, which I can write as secant theta. And I'm going to leave it at that. Okay, so if possible, it's good to solve for r. So this parabola can be represented using this polar equation, r equals 4 tangent theta secant theta. All right, so in the next section, we're going to, start looking a little more closely at like, okay, what is the connection between this equation and this curve if we're thinking about polar coordinates, right? So we're going to start to understand the relation between polar equations and polar graphs, and we're going to end up with some really, really cool results. So don't miss section 8.2. I'll see you over there.